So for the mechanical system, we said that the main elements are the mass spring and the damper are our main things. So our very basic system is this mass spring damper system, which is like this one, which represents many and there might be some forcing, and there is the displacement x of t. So such systems, many systems we have in real life can be approximated by some system like this one. Let me just, this is too thin, so let me do it this way. So we try to model them, the dynamic behavior of the system using basically the kinetic energy storage, which is mass, the potential energy storage, which is springs, and then we have the dissipation, which is represented by dampers. We try to model them using these three elements. The real system might not look like this one, but we eventually try to reduce it to something like this. And not all systems can be reduced to this one. By the way, please turn off your sounds, whoever is this. Please turn off your microphones. There might be some multiple mass systems in which every system has, well, a system has multiple masses, in which case we have one mass spring, another mass, another mass, etc. M1, M2, M3, etc. What we do is we basically write summation of the forces equals mass times the acceleration for each mass. Okay, this is our main method. The mass time, the Newton's second law applied to every mass basically gives us the equations. And then what you remember that we have the S operator. S is something like that replaces the d by dt, so that our differential equations can become converted to algebraic equations, and then substituting them to one another, we can find the so-called transfer functions of the systems. We also said that there are rotational equivalents of all these things. For example, if you have a rotational thing, that you have a torque is applied and this thing rotates with theta, and if this thing has an inertia of I, the summation of all the moments is equal to I times theta double dot is the equation for the rotational case. And we might have combined translation and rotation, in which case you have the kinematic relationships. For example, you might have, if you have no slip here, like here, let's say this is R and this is rotating with theta. If this thing moves with X, the kinematic relationship is equal to X equals R theta, if there is obviously no slip in your system, okay? And you
Hocam, can I ask a question?
Yes.
Hocam, in the real life, there is always no slip, right? No slip condition or not?
No. Well, there is always, in most cases, actually, there is a little bit of probably a slip. No slip is a kind of an approximation. there will always be some kind of slip, probably. No slip is an ideal condition, but it is a good approximation. The thing is, when there is no slip, actually, for example, if you have a car that is going on the road, the no slip condition means that there is no energy loss because of friction. First of all, no slip requires friction. Without friction, there will always be slip, okay? And no slip, in the condition of no slip, you can show that there will be zero energy loss. So in the cars that are traveling on a road, there will be zero energy loss because of the tire friction if there is no slip, which is kind of true. Most of the energy loss in a car is actually because of aerodynamic drag. It is not because of the tire friction, but there is some tire friction, and that is because there will be a little bit of slippage in the car's, wheels as they go through the road. There is a little bit of slip, but not much, but there is some. So no slip is an ideal condition. But in any case, for our case, the important thing is that the kinematic relationships are imposed by the no slip condition. Okay. Secondly, so we have for our equations, we have the constitutive equation, which is constitutive, let's say, equation. Summation of all forces is equal to mass times xi double dot, okay? Let's say fi, I equals, let's say, 1 to n masses you have. And then there are the kinematic equations.
Hocam, may I ask something?
Yes.
I'm sorry to disrupt you, but if there is slip, we just need to subtract from the x, right?
Well, if there is slip, this condition is not valid. X equals r theta is not valid. And your system is going to be a 2 degree of freedom system.
So like, we just can't make like x equals r theta minus like something, the slip condition.
What is that something? We don't know what that something is.
Yani şey gibi dedim hocam, işte teker bu kadar dönünce x kadar gidiyor diyoruz ya. İşte
Yeah.
o kaymayı x'ten çıkartırsam
You
işte
can say that, but you cannot find that quantity, that extra quantity.
okay.
You will say that if there is slip, x and theta are independent coordinates. So those coordinates are not related to each other, and each has to be solved separately. By the way, the constitutive equations can also be summation of moments is equal to I times theta I double dot also. Okay.
Hocam, what about for the acceleration and velocity, we take the derivative of the equation that we have no x is equal to r times that theta.
Yes.
So if we have slip, there will be is it going to be constant or not? Because if it is constant, derivative of it will be like nothing, will be zero. So it will be not affected. Is it constant, the slip, or not?
Okay, I don't want to go into this. Is a question of dynamics. You know, you should have learned this in the dynamics class. But anyway, let me repeat this a little bit. If there is no slip, you have x equals r theta, right? This is theta, and this is x, right? If there is slip, x won't be equal to r theta anymore. Well, but how about the friction force that we have here? There is this friction force F that is applied by the rod. If there is no slip, the friction force is kind of unknown, okay? Friction force is an unknown. It has to be less than mu times and etc., but it doesn't matter. But basically, we don't know the friction force. But if there is slip, the friction force is equal to, if you assume dry friction, you know the friction, the quantity of the friction force. Now, here you have, if there is no slip, this is your equation. If you have slip, this is your equation, okay? In each case, you have something to work with. Here, the number of coordinates is decreased by 1. Here, the friction force is known. But here, in this case, the friction force is unknown. So the problems are still solvable. In each case, only the conditions are different. Okay?
Thank you, hocam. Thank you so much.
Anyway, so let's continue. So basically, sorry. Maybe this is better to write it in the thinner. This is too thick. Combining, let's say, constitutive and kinematic equations, we get the equations of motion. You might have looked at the videos, or not the videos, sorry, the PDFs, that is the presentations of Samim Hoca from ODTÜ. They use, in Ankara, they use a kind of a equivalent but different technique in which they have the continuity equation and the constitutive equations and so on, but those are, I think those are a little bit confusing in your level, so I try to keep it kind of simpler and try to introduce the equations like deriving of equations like this. We basically write F equals ma, moments equals I alpha, and kinematic conditions like x equals r theta. If you combine them, you get the equations of motion. You can always get the equations of motion. Okay? I think this is the simpler way of doing things. Another possibility, another thing we should look at is the equivalent, let's say, quantities, let's say masses, spring, damper, etc. Let's say that you have again, supposedly a circular disk that rotates without slip. This is x, and let's say that there is a force F acting. If you remember the equation of motion, I have derived the equation of motion here. This is m, this is r, this is I, etc. The equation of motion was m plus I over r squared x double dot plus kx was equal to f, as you might remember. Now, this quantity is not the mass of this system, but it is the equivalent mass. Because if this were a simple mass, not a rotational mass, the equation of motion would be mx double dot plus kx equals f. Here, therefore, the equivalent mass of this system is x double dot. On the other hand, for example, if you have two springs connected like this, let's say K1 and K2, if these springs are parallel, let's say this is, you pull it with an x, f, and this is x. Obviously, f is going to be equal to K1 plus K2 times x. So you can say that this is the equivalent spring of this system. And similarly, if you have, for example, let's say this is fixed. If you have two springs that are in series, you can guess that. It's not easy, hard to find out that f equals, what will that be? K1, okay, which is K equivalent, which is 1 over K1 plus 1 over K2 inverted, for example. Okay. So we can find the equivalent masses, equivalent springs, etc. of a system under these conditions. They don't have to be, there might be more than one mass and spring in the system, so that we can find the equivalent quantities. There are, masses, springs, and dampers are quantities that we commonly use, but there are other mechanical devices which we call the mechanical transformers. These also exist in mechanical systems. What are they? They are things like gears, levers, for example, cams, and there are others. We don't really care. The most important ones are the gears and levers that are what we are going to use. Basically, they transform the motion at the input to a related motion at the output. So basically, you have, for example, output in these things will be equal to some kind of transformation ratio. Let's say transformation ratio times the input will be. So O is equal to some kind of, let's say, T times I. And T being usually this is a constant, okay? At least for the case of gears and levers, it's a constant. For cams, it's a little bit more complicated. We won't go into that. Well,
Hocam, is it theta?
No, it's not theta. It is the output, O.
Oh, okay.
Okay. For example, if you look at gears, gears are important for us, so let's spend some time on it. Let's say that you have a gear like this. There is an input shaft, and this one didn't work. Actually, sometimes this thing gives you a good ellipse, sometimes it doesn't. Now it did, okay. So this is the output shaft. So this is T, the torque omega 1 and theta 1. So the gear has teeth on it. This second one also has teeth on it. They have diameters. Let's say this has a diameter of d1, this has a diameter of d2, etc. It doesn't matter really. This has theta 2, omega 2, T2. You know, torques, both rotations and forces, that is torques, are transferred from one gear to another one. We define the gear ratio to be the ratio of the diameters, d2 over d1, which is actually equal to the number of ratio of the number of teeth is also n2 over n1. If this is the number of teeth, well, let's call it the gear ratio as n. Since the velocity at the contacting tooth are the same, velocity at contact. So let me draw it here. This velocity, whatever it is the same for both ends. So it would be d1 over 2 times omega 1 would be equal to d2 over 2 times omega 2. So these 2's cancel. d1 omega 1 equals d2 omega 2. So omega 2 over omega 1 will be, what will that be? d1 over d2, which is 1 over n. Right? And since we assume usually that there is no power loss, that's an assumption, but usually it's approximately correct. T1 omega 1 equals T2 omega 2, which says that T2 over T1 is equal to omega 1 over omega 2. Omega 1 over omega 2 is, well, here from it is n. Okay. As you see, we have the torques are related to the gear ratio. For example, if you have a larger gear, the speed decreases. If D2 is larger, the speed decreases, but the torque transmitted increases. That is the idea used in the gearboxes. Okay. The second thing is the lever, which is also commonly used. Let's say something like this. Let's say this displacement is y, and let's say this displacement is x. Well, it is kind of similar to gear actually. F1, this is F2. Okay. Levers basically are used to change the direction of the forces and also the intensity of the forces. Okay. This thing, let's say, rotates with the angle of theta. We can say that, by the way, we can say that this distance, let's say, is A, and this distance is B. Okay. We can say that x is equal to A times theta. But for small displacements, yes, you can say that y is equal to E times theta. So if you divide these to each other, you will get x over y is equal to A over B.
Hocam, can I ask a question?
Yes.
In the external mesh, aren't we taking as minus the velocity relation of the velocity with the diameter?
What are you talking about? The gear?
Gear, yes, hocam.
Yes, but what we are doing here is we define omega 1 as, let's say, looking from here as clockwise, whereas omega 2 as counterclockwise. Okay. In the 301 class, we were defining everything as counterclockwise. Here, we have the luxury of defining the direction as we please. Okay. So if you define the directions as you like, you can do it this way.
Okay, hocam, thank you so much.
Here, I define x downwards in the lever and y upwards, okay? So that I can write this x over y equals a over b. If I had defined everything upwards, there would be a minus here. Do you understand?
Yes, hocam, thank you so much.
Okay. So the x over y is equal to a over b. And also, you can say that x dot over y dot, the velocities have the same ratio, a over b. And also the work done, which is force times displacement, or you can say the energy or the power, F1 times x is equal to F2 times y. So you can say F2 is equal to, what will that be? X over y F1. So which is F1, okay? So you can say, for example, if you define this A over B as the transformation ratio, you can say that X is equal to ny, okay? Well, maybe I should really, this is confusing. Let me just change this a little bit. This is F1 and F. Let's use Fy and Fx here so that it is Fx, Fy times y. X is equal to my, and then Fx is going to be 1 over Fy, I think, if I'm not wrong. Right? Fx is going to be, yes, d over a. So this is the transformation equations for our system. It is kind of similar for the gears. Torques and displacements are inversely proportional. Okay. Now we can define how much time we have. Okay, we have
Hocam, what is N again?
n is a over b, the ratio of a to b here.
Oh, okay, thank you.
The equivalent systems, let's say. Let's say that you have a system with a gear, like this. This is a gear connected to another gear. And here at one end, you have an inertia, I. Okay. So this is T1 is applied. This is omega 1. And you have a gear system with a ratio of n. This is our system, let's suppose. Okay? We want to find the equivalent of this. And this thing rotates with, let's say, omega 2. This should be equivalent to omega 1. I should be using, okay, I can use it this way. Omega 1 and T1 applied on I equivalent. Okay. So we want to take the gear system out of this equation. And we want to define an equivalent inertia for this system. Now, the kinetic energy for this system, as you know, is 1 over 2 times I times omega 2 squared. Okay? But omega 2, from our definition, what was it? Omega 2 was omega 1 over n, right? So the kinetic energy can be written as 1 over 2 I times omega 1 squared over n squared, which is 1 over 2 I over n squared omega 1 squared. Now what is this? This is the equivalent inertia, I equivalent. So the equivalent inertia for a system is I over n squared. And similarly, if you have, for example, a gear connected to for some strange reason, to a torsional spring like this. Okay. Let's say this is omega 1, T1. This is omega 2. Here you want to find the equivalent spring constant, like let's say, of this system like this. With a gear. This is omega 1. But omega means theta here, by the way, T1. Here, the stored quantity is the potential energy, which is 1 over 2 kT times theta 2 squared. So, which is 1 over 2 kT times. Well, theta and omega have the same relationship. For example, this is theta 1 over n squared, which is 1 over 2 kT over n squared theta 1 squared. So the equivalent spring of this system, for example, kT equivalent would be kT over n squared. So that the spring constant of the system equivalently decreases. Also, the inertia equivalently decreases when you use a potential energy. And similar things happen when you use a damper, actually. You have BT equivalent, for example, would be BT divided by n squared, if BT is a damper. Okay. So gears are usually used in, well, devices, machines, for things like, for example, robots, to reduce the effects of inertias, okay? The effect of inertia is usually reduced if you do that. How much time? We don't have too much time, I suppose. Let me just do one example. We don't have time for anything else, so let's do a simple. Okay. Now, here okay, there is also the possibility of using, let's say, theta as our coordinate. So what we want to do is equation of motion in terms of x, y, and theta, okay? In terms of x, it's trivial. By the way, yeah, let me write the equation of motion in terms of x. For x, the lever, by the way, we assume that the lever has no mass, zero mass, okay? So it has no effect on the motion. So the equation of motion is mx double dot plus bx dot plus kx equals f of t. We can directly write that. Another thing is, even if there is some gravity, we can write the following equation. This you should remember from Mech 301. I don't want to spend time here. You can assume that the x is measured from static deflection, and the effect of gravity is taken into account by the static deflection. Okay, so that we don't really care about the deflection because of gravity. We don't care about the gravity term. So this is the x equation. For y, we can say that x is equal to, a over b times y. Okay. Again, we can equate the kinetic energies. For example, the kinetic energy is, for deriving the equivalent quantities, this is the easiest way, for example, mx dot squared, which is 1 over 2m a over b squared y dot squared. So the equivalent mass for y is m times a squared over b squared. The potential energy is similarly 1 over 2 k times x squared, 1 over 2 k over b squared y squared. And the power dissipated, again, power dissipated, let's say, power is Ex dot is the damping force times x dot, which is bx squared. So it will be b times, again, a over b squared y dot squared. So that the C equivalent will be, B equivalent will be yeah, so I used B and B together, right? Which is a problem. Okay, I should be using C, I suppose, here. Where else is here? In each of those cases, we have a squared over b squared. But the work done by F is Fx dot, and that is F times A over B y dot. Okay, so that the equivalent force is going to be F times A over B. So the equation of motion in y coordinate is going to be something like this. If you do everything together for y, m equivalent y double dot plus c equivalent y dot plus k equivalent y is equal to f equivalent. But if you do carry everything together, what you are going to get will be something like this: my double dot plus cy dot plus ky. These are not the equivalent quantities, but then you will have e over a, not a over b, but b over a, because you have all these things squared here. And those squares are going to cancel the other one, and that the remaining will go here, repeated, which means basically this thing is carried to here as b over a.
Hocam, can I ask a question?
Yes.
Hocam, can't we just plug, we know that x is equal to a divided by b times y. Can we just plug the number into the x? Because
Yes,
it
we
gives the
can.
same answer.
Yes, it should. If you do things correctly, it should. But I'm trying to introduce the concept of equivalent mass here.
Okay, I got that. Thanks so much.
Okay, and for the coordinate theta,
Hocam, may I ask something?
yes.
So, about power dissipated. So, may you explain how we find it? Because when I look our notes, I just find we need to make V1 minus V2. So, like,
Okay, now this is Cx dot is the damping force. Damping force times the velocity. Force times velocity is the power. Okay? That's how we
but
huh?
şey hocam,
Yes,
when
but I know what you mean, but here one end, by the way, this is C. This end is like, this end is fixed, so we don't have any motion here and at one end. And at the other end, the motion is X. So it is C, it's C times X dot.
So isn't it needs to be, okay, C times X dot square. Isn't
Yes,
it needs to
eventually it becomes Cx dot square.
Okay.
And for the coordinate theta, the equation of motion would be I theta double dot rather equivalent plus C equivalent theta dot plus K equivalent theta equals, what should we have? Let's say T equivalent. Okay. So the kinetic energy, which is 1 over 2 mx dot squared, is 1 over 2 m. X dot is a theta dot. So a theta dot squared. So it is 1 over 2 ma squared theta dot squared. And this is the I equivalent, therefore. For potential energy, we have 1 over 2 kx squared is equal to 1 over 2k. Again, a theta squared, which is 1 over 2 ka squared theta squared. So this is k equivalent. And similarly, you have C equivalent is Ca squared, and the T equivalent would be, actually it's very simple, force times the A. Okay. That is the torque that you would be getting. And the equation of motion is going to be, what is it going to be? So you can cancel the A terms, etc., and find the result. I tried to explain the concept of equivalent. This is I equivalent, etc. Okay, this is C equivalent. Okay, I'll continue with this a little bit more the next time, and then we will be done with the mechanical systems, hopefully. Let me stop the recording.